Okay, so back when we learned about what a function was in Unit 1, we talked about functions as if they were machines, right? So remember we talked about like, okay, what types of machines do we use in everyday life that like take something in, change it somehow, and then give us out something else. So we talked about like a freezer, you can put in water, it can freeze it, you'll get out ice, or a toaster or something like that. So just to kind of refresh your memory, that's what we thought of as a function. It takes something in, it does a set of operations on it, and it gives us out something else. So today we're going to talk about an inverse function. And the goal of the inverse function is to undo what the original function does. So basically what it does is it will do the opposite operations of the original function, and it does them in the opposite order. So if you imagine like our example of the freezer, imagine a reverse freezer, an inverse freezer, where you put in ice, it melts it, and then it gives you the water. That's basically what an inverse would be of that, right? So opposite operations in the opposite order. Here's the notation that we use for an inverse function. It almost looks like an exponent, but it's not. We use f inverse of x. So that's how we read it. Okay, so one important thing is that this is not an exponent of -1. Okay, so that's the really important piece here, is that this is not an exponent. The -1 is simply a notation that we use to indicate that this particular function is the inverse of the f at x function. And of course, we know we can use different names for functions. So if it's g at x, we can say g inverse of x. If it's h at x, we can say h inverse, and so on. So because this is not an exponent, we know that f of f inverse of x should not be equal to 1 over f at x. Okay, so we're not allowed to use the negative exponent rule and bring this down and then make the exponent positive. So these two things are not equivalent. So we need to kind of separate the idea of this being an exponent versus this just being a notation. Okay, why they use it like an exponent, I do not know. I wish that it was not that, but it is, so not the best decision. Whoever decided, I don't know. Okay, so let's start with something simple. We have f at x equals 2x plus 3. So what are the operations in the order that we would do them for this function? What would we do to x first in this function? What does this tell us to do? We would follow BEDMAS, right? Blair? Okay, so multiply by 2. And then second, what would we do? See ya? Add 3. Okay, so that's what f at x does. So the inverse function needs to do the opposite operations to this, and then also it wants us to do them in the opposite order. So the first thing that I would need to do for the inverse function is I would need to do the opposite of the last thing that I did in my original function, which was I added 3. So what's the opposite of adding 3? Josh? Okay, so the inverse function will first subtract 3. And then it will do the opposite of multiplying by 2. So obviously that's going to be dividing by 2. So opposite operations in the opposite order. So because I added 3 last, I'm going to subtract 3 first with the inverse. We just have to make sure that we set up an equation that works properly with BEDMAS. So f inverse of x. Any ideas what this function might look like if we have to first subtract by 3 and then make sure that we divide by 2 last? What would this look like with x in it? Ella, what do you think? Yeah, basically we can do that. We don't even really need the brackets necessarily. Like if we have this on top and it's all over 2, that will, like we would know to subtract 3 first and then to divide 2. But if you want to put the brackets, you can put the brackets. That's fine as well. So this is the inverse operation, or it's the inverse function of f at x. So it should theoretically undo everything the original function does. So we could perform a check here. We could say, if I plugged in any x value into f at x, and then I got out a y value from that, if I plug that y value into my function, into my inverse function as x, it should give me back out what I started with if it actually undoes the original operations. So Chris, choose me an x value that we can check. Any x value, 7? Okay, so we're going to evaluate f at 7. So using this function. 2 times 7 plus 3 should give me 14 plus 3, which is 17. Then I'm going to try, and I'm going to plug in 17, what I got out, and I'm going to see if it gives me back what I had put in originally. If it does, then I've done it correctly. If it doesn't, then there's something wrong with my inverse. So if I evaluate f inverse at 17, what I got out from my original 7, I'm getting 14 over 2, and this gives me out 7. So did I get what I started with? Yeah, so this is good. All right, so when the function's a little bit easier, something like 2x plus 3, we could probably figure out like what this equation looks like just by kind of doing what we did up here, which is like, I figure out the order, I figure out what operations are happening, I switch the order and I switch the operations, and then I kind of come up with an equation. As functions get more complex, this is a little bit more challenging to do. You can still do it and try it. But this is like a little kind of like algebraic method that you guys can use to find the inverse function. So it's pretty simple, actually, very straightforward. So we're going to replace any function notation that we see with y instead of like f at x or g at x or whatever. We will swap all of the x's and y's, and then we'll get y by itself again. So re-isolate for y, and then we'll use our inverse notation again. So replace the function notation with inverse notation. Okay, so what does this look like in an actual question? So let's see how we would have done it with our function above. Is it break? Okay, so let's go on break and then we're going to use the steps above to apply them to the function that we just figured out the inverse of. If you guys have cell phones out, those can be stored away now, please. All right, so first step, replace your function notation, whatever that is, with y. So first thing I'm going to do is I'm just going to replace f at x with a y. You know those are interchangeable. Okay, second step, swap all x's and y's. So wherever you see an x, replace it with a y. Wherever you see a y, replace it with an x. Third step, isolate for y. So we're going to start by essentially when we isolate, we do reverse BEDMAS, right? We get rid of additions and subtractions, then multiplications and divisions, then we can go into exponents and brackets. So we're going to move the positive 3 over as a first step.
And then we will divide each side by 2. And now we have y by itself. Just going to swap the sides there. And then the last step is you're just going to replace y with inverse notation. So because I started with f at x, I'll replace y with f inverse of x. Okay, so as you guys can see, we got the same thing that we had figured out above, but this is more of like a mathematical process to do that. It's also more helpful as your equations get a little bit more complex. This process will kind of make it a little bit easier. Yeah, so we ended up getting the same function that we figured out. All right, so we're going to find the inverse function of a couple different functions here, just so we can kind of get the hang of the process. If you can figure out the function without necessarily having to do every single step of what's listed here, if you can figure it out kind of like what we did here, that's totally fine. But you should at least practice the process a little bit, just especially with the more complex equations, just so that you can make sure that you know how to find it using the steps. So I'm going to use the steps just so that we can practice. We're going to replace function notation with y. Miguel, can you just shut the back door for us there, please? Okay, so replace function notation with y. That's the first step. Second step is swap all x's and y's. So we're going to replace x's with y's, y's with x's. And then we want to just get y by itself again. So what would be the first thing that I would do to isolate for y here? What would I move? Maya? Okay, we'll multiply by 4. These will cancel. So we'll have 4x equals 3y. And then we'll just have to divide that 3 out. And then final step, now that the y is by itself, we will replace y with inverse notation. So because we started with g at x, we'll replace y with g inverse of x. Matt, can you just put your headphone away there? Okay, so that's steps 3 and 4. Okay, so does this function do the opposite operations in the opposite order of the original function? What does the original function do first to x? It multiplies by 3, and then what? Divides by 4. So we should see that the inverse function, what does it do first? Multiplies by 4, then, so is this what we would expect? Is this opposite operations in the opposite order? Yeah, so it's good. Yep. Yeah. So I'm actually following this algebraic process right here. So the second step asks to swap all x's and y's. And the reason why we do this, guys, is because when I swap the x and y and then I try to get y by itself again, basically this is telling me that I have to, when I go through the process of moving everything to the opposite side of the equal sign, it does reverse BEDMAS. And it's going to create the opposite operations in the opposite order. That's basically why we do that. Because as I isolate, it's going to undo all those operations that are on the right-hand side of the function. And then I'll get all of the inverse operations on the other side, right? Okay, let's try B. So first step, replace function notation with y. Second step, swap x's and y's. And you could probably figure this one out without necessarily having to follow along with the steps, but that's practice. Okay, what's the first thing that you do to get y isolated here? Okay, this is just grade 9 now, right? At this point, just isolate for a variable. Chris? Okay, we'll bring the 3 over. And then we'll just divide out that 4. So the whole thing gets divided by 4. Okay, and then last step, we're going to replace y with inverse notation. So it'll be h inverse because I started with h at x. So that will be our inverse function. Okay, let's try a couple more. We'll get to a few more complex ones. Okay, so let's follow along with the same process. So switch f at x into a y. Swap your x and y. And then let's get that y isolated. So I'm going to bring the 1 over to start. I'll get x plus 1. And I get rid of a squared by doing what? Where? I have to square root. Okay, so here's the thing about finding an inverse function when I do the square root. So let's suppose I have an equation that's like, you guys don't have to write this, but let's suppose we have y squared equals 16, and I'm trying to solve for y, right? When I take the square root of each side here, we know that there's one obvious answer here. What's the square root of 16? But there's actually 2 answers, isn't there? Oh, there's plus and minus 4. Positive 4 squared is 16. Negative 4 squared is also 16. So when I'm doing a solving process and I undo a square by doing a square root, I actually would have to put plus minus in front of that to get both possible answers. So what I do is when I go to do the square root of this side, I actually put plus minus in front of it so that I actually get both of the answers, positive and negative 4. Now I only do this in a solving process and in an inverse process. So if ever I have to undo a squared by doing a square root when I do the inverse, I'm going to put plus minus in front of it so that I make sure I get both of the possible answers of this. Okay, makes sense? So when I go to square root, I'm going to make sure I put plus minus in front. This side doesn't really matter because those will cancel anyways. So you don't have to put plus minus in front of that other side. Yeah, Chris? No, because that I'll still have a y inside there. So we want to get one single y isolated alone on one side in the end. Okay, so that's kind of the idea behind the plus minus. So anytime you're isolating, just make sure that if you're undoing a squared, that you put a plus minus in front of your square root. So we'll be left with f inverse of x equals plus minus x plus 1. All right, let's do a couple more. So first step, we're going to replace y or replace function notation with y. The square root of this is only going to go over the x here, just what's in brackets there. Swap x and y. And then begin to isolate for y. So what moves first if I'm isolating for y? Chris? Okay, perfect. So x minus 2. And then I get rid of a square root by doing what? Okay, so I have to square it. So whatever I do to one side, I must do to the other. So I'll square both sides. These will cancel. And then we're going to be left with r inverse of x is equal to x minus 2 squared. You can leave it, just leave it in factored form. You don't have to expand it or anything like that. All right, so once you've done the first couple steps of this process, it's basically just, we're taking it back to grade 9, right? When we worked on like algebra and isolating variables and stuff like that. So you guys know how to do all of this. It's just really kind of getting the process down of like swapping the X and Y and then getting it isolated. Okay, I want you guys to try E and F, see if you can get the inverse functions of those ones. We're getting a little bit more complex here. So see what you can do with that. For F, the square root just goes over the up until the end of the bracket there. Okay, and I'll start putting up my answers in a couple seconds. Okay, so the answer for the first one is up. You guys can check. And I'll give you a second to finish F before I start putting my answer for that. Okay, so there's the first few steps there. We swap out G at X with Y. We swap the X's and Y's, and then we're going to start isolating. Before you touch anything underneath a square root, you have to almost imagine that underneath the square root is brackets. And with BEDMAS, brackets are the last things that you would touch if you're doing like isolating, right? Because you're doing reverse BEDMAS when you isolate. So you get rid of additions and subtractions first, then multiplications and divisions, then exponents, then you can go underneath the exponents into any brackets that are there. So if I see a square root, it's almost like understood that there's brackets underneath that. So you have to get rid of the square root before you get rid of that -1/2 underneath the brackets. So we'll do that by squaring each side. So I have to square this whole thing on the left-hand side. The root and the squared will cancel. I could actually, just to like simplify this a little bit more, I could actually apply the squared to both the top and bottom here. That would leave me with x - 3 squared over 4. And you'll kind of see why I'm doing that in a second here, because we're left now with -1/2 y. And there's a really quick way to get rid of a bracket, or sorry, not a bracket, a fraction. When I'm trying to get rid of like something like a fraction of a half, we might be tempted to divide each side by -1/2, but then I'm going to have to flip and multiply, and I don't really want to do that because I'm going to have a fraction inside of a fraction. So anytime you see a fraction that you have to get rid of, or you want to isolate out of one side, just multiply by the reciprocal on each side. So what happens when I multiply by the reciprocal on each side here is I multiply by technically 2/1. And then the negative and negative will cancel, the 2 and 2 will cancel. So I make sure I do that on each side. I basically multiply that in. So if I had something like, let's say, maybe I have 5 = 3/4y, you don't have to write this. If I wanted to get rid of the 3/4 really quickly, I'll just multiply each side by 4/3. Okay, so do you guys see how that works? So basically what would happen on the right-hand side is 4 and 4 will cancel, 3 and 3 will cancel, that 3/4 is gone. Okay, so that's the quick way to isolate and get rid of a fraction like that, multiply by its reciprocal. Matt? I just applied the squared to the top and bottom. And the reason why I did that is because now we can actually reduce here. So I'll reduce the 2 and the 4 to 1 and 2 here. So we'll just be left with -x - 3 squared over 2. Well, the negative is here. So I'm just going to write it where it was, right there. So yeah, just keep the negative. Okay, or alternatively, sorry, I shouldn't have an equals on this side. Alternatively, you could also write this as like -1/2 x - 3 squared, like so. Okay, so either one of these is acceptable. All right, so I'll just leave it. We're gonna replace, so final step, replace the y with function notation, G inverse. Josh? Like this part? Yeah. Yeah, so Right, so you see how we multiplied by the reciprocal here, right? And then we reduced, so we were left with 1/2 here. So that's why I'm saying we have 1/2 there. It's not from the multiple of getting rid of this. Does that make sense? Okay. So that one, if you could do something like that, you could probably do any of them. Like that one's probably one of the more complex type ones. The challenge one, I'm not going to give you anything like that, but if you want like a little extension question, I'm happy to check it if you want to try it. But yeah, I'll just leave that there for you guys if you want an extension on that. And let's talk about graphing. So finding an inverse by graphing. So we kind of understand what an inverse is algebraically. It does the opposite operations in the opposite order of the original function. We talked about the algebraic way that we can figure that out. Graphically, what's happening with inverse functions is they are being reflected over the line y equals x. So imagine that we took this and we sort of folded our paper over this diagonal line y equals x. So this is the line y equals x. It's the most simple line that you guys learned about at the beginning of grade 9, right? You just learned about like what is the most simple possible line that we can have, and that's what it produced. Okay, so basically what we have here is we've got a circle at the point. What point is this? 1, 1, 2, 3, 4, 5, 6, 7, 8. So we've got a point at 1, 8. We have a heart at the point -3, 4. And we have a star at the point 1, 2, 3, 4, 5, -5, 1. Okay, the inverse function. So if we assumed that this was our regular function, the inverse of this is going to swap things, or it's going to reflect things over that line, almost like we fold the paper over, right? What ends up happening is that the x's and y's end up swapping. So the inverse function, we're going to have a circle at the swapped version of this, so at 8, 1. So that's going to happen 1, 2, 3, 4, 5, 6, 7, 8 here. I'll do an outside of blue. It's like inverse. Okay, so 8, 1. And then we're going to have a heart at 4, 3, or 4, -3, I should say. So 1, 2, 3, 4, 1, 2, 3. And then we're going to have a star at -5, or sorry, at 1, -5. 1, 1, 2, 3, 4, 5. Here's our star. So basically, we're just swapping the x and y coordinates. How does that connect back to what we just did algebraically? How does that connect back to that set of steps that we use to find the algebraic inverse, swapping the x and y's? Chris? So well, yeah, the x's and y's are in the opposite order. And also there's literally a step inside of finding the inverse where we swap x and y, right? So that's actually what's happening graphically as well. So to get the inverse, let's make ourselves a note here, unless, did I write it on here? No, I didn't. Okay. To get the inverse function, or the inverse graph, I should say, maybe, simply swap the x and y coordinates. Of the original function. It's not a vertical reflection. It's kind of like a diagonal reflection. Vertical reflection would just be like this would flip down. It actually kind of flips like diagonally over this line. Okay, so box this up, highlight it, something just in case you're looking back and you need to find what an inverse function does. So notice that I did not change any signs of anything, right? I simply made the x's the y's and I made the y's the x's. I literally just swapped their order. Okay, so don't switch the sign of anything. Okay, can I scroll? Everyone's good? Okay. So we're going to quickly do a couple graphing things here, and then you guys will have some time to practice this on your own. Okay, so we're going to sketch the inverse of one of our parent functions, f at x equals x squared. So let's start with that. I'm going to do some points. Some good x values would be -2 to +2. And we said once we square them, we'd get 4, 1, 0, 1, and 4. So that's what we're going to start with. I'm going to put it on the graph just so that we have a visual as well of what we're doing here. Maybe we'll also just scale this quickly. Okay, so there's the parent function. Inverse function. I don't even need to find the inverse equation in order to do this. If I have the points of the original, I'm just going to swap them and then I'll have the points of my inverse function. So I'm going to make the x's into the y's and I'm going to make the y's into the x's here. Literally just swapping the columns. So 2 points actually remained the same, 0 and 1, 1, 0, 0 and 1, 1. We have 4, 2, got 1, -1, and 4, -2. And I'm going to label that one as F inverse. Okay, so this is kind of interesting. If I erase this half of the graph, what's this? That's the parent function square root of x. So what's the opposite of squaring something? What's the inverse of that? Square rooting. So where do I get this bottom part from though? Square root of x, but what do we know when we undo a squared in something? What did we talk about in the inverse process, Maya? Okay, plus minus. So that's what gives me that bottom piece, right? The plus minus. So when I do the inverse of x squared, I square root and I have to do plus minus as we talked about, and I get the top part, which is the positive part, and I get the bottom part, which is the negative part. So that's where we get that bottom piece. Okay, guys, so if you're asked to do an inverse function on a graph, and I don't ask you to like calculate the equation or anything like that, all I'm expecting you to do is you do everything that you know how to do from the very beginning of transformations. Start with the parent function, do your transformations, and then if I also ask you for the inverse function, just take that transformed table of values that you have and swap the coordinates and graph them, and you're good to go. You've got the transformed inverse function. Chris? Most of the time, I'm not going to ask you to find the equation when I ask you for a graph. I might ask you both, like I might put a part A, find the equation, and a part B, graph it now. But yeah, if I don't ask you for the equation, you can just graph it as, like just label it as the inverse. But yeah, if you have the equation, you can go ahead and list the whole thing. Okay, so here's a sample of what I was talking about. This is actually, I think, one that we did from earlier above. So we actually did already find the inverse of this, but let's suppose we never found the inverse equation for this. What's the parent function of g at x? What's the base function that I would start with for this? We had three options really. We had x squared, square root of x, and we did 1 over x. So out of these three options, Blair? Okay, so that's our parent function, right? I'm going to start with f at x equals square root of x. And we'll start with the parent function points as usual. I'm ignoring this for right now. I don't really care about the inverse at this point. I just want to get the original function graphed. So 0, 1, 4, 9 as the parent function points. We talked about how these ones are good ones because we're going to square root them to get our y's, right? So square root of 0, 1, 4, and 9. And then we're going to do g at x. So what do we have out of AKDC here in the g at x function? This one kind of already has the equation combined, right? It has the parent function and the transformations together already. Yep, so I'm just asking right now, what is A, K, D, and C? Maya? Okay, perfect. So we have an A, a K, and a C. And when we set up the equations, what should we get here? Okay, just same as what we've been doing all along. See ya? Very good. Okay, make sure you do the reciprocal of K here. Okay, so let's take all of our X's and we're going to multiply by -2. And then we're going to take all of our Y's now. We'll multiply those by -2 and then also add 3 to them. Oh, I did that wrong. -1, -3. Okay. We're just going to graph this to start. We're not going to graph the parent function because it just says graph g at x and g inverse of x. So let's just do g at x onto the graph here. I'm going to do a scale. Let's say we'll do the y's by 1s and I'm going to do the x's by 2s. Just so that we can fit that -18 point on there. Oh, actually, because we're going to do the inverse, we'll have to do the scales the same for both of them. So let's go by 2s for everything. Sorry. Okay, and I'm going to do down here with the y's as well, because we'll need some points down there when we do our inverse. Okay, that should be good. Okay, so 0, 3 to start. That's here. -2, 1. -8, -1. It's like right here. And then -18, -3. Okay, so there's g at x. I'll just label it as g at x because this is already fully done in the equation there or in the question. Okay, so this is the same as everything that we've been doing so far, right? Nothing new in this question. Now, if I want to do the inverse, all I'm going to do is I'm going to take these points from g at x that I figured out with transformations, and I'm going to swap the x and y coordinates. So I'm going to make the x's the y's and the y's the x's. And then we'll graph them. Okay, so over here, and if I've done it right, it should look like if I fold over that diagonal line, that it looks symmetrical diagonally. So no like extra calculations needed or anything like that. Like I don't even really have to come up with the equation of g inverse of x. All I'm doing is I'm just taking my transform points and I'm swapping the coordinates and then I have the inverse graph. That's all I need to do. Okay. Unless I'm like literally asked to find the equation, then obviously I'll do some more work for that. But this one doesn't ask you, it just asks you graph g inverse of x. So once we have g at x, should be really easy to come up with the graph of g at x just by swapping those coordinates. Okay, I'm telling you this and I'm repeating it a couple times because without fail, I'll usually have a couple students that will go through like a whole process of trying to find the equation of g inverse of x, even if I don't ask for it. If I just ask for the graph, just swap the coordinates, graph them, and you're done. Okay. Sometimes if you have a graph that's like halfway over this line, it might look kind of weird when you reflect it because a piece of it comes up here and then parts come down like this. So you might find that it overlaps a little bit if your graph is already crossing over that line. So don't be worried if you see something like that. Okay, any questions for inverse functions? Sure.